Alright, so we're going to start today talking about the actual first law of thermodynamics. Now, the first law of thermodynamics literally states that the change in internal energy for an object or for a gas is going to equal the heat added into the situation minus the work done by the situation. Now, one thing that is important here is to notice what's going on here with the term W. Alright, up until what we have done now, every single time that we have used W, we have done work as work done by. Okay, now what is going to be changing is there's two different ways that we're going to be looking at work. There may be work done by an object, and there may be work done on an object. Right, the difference between the two is actually significant. The good news is it normally just means the difference between a positive sign and a negative sign. But it may actually change up and be based upon some different situations here. Okay, now the first law is actually pretty simple. The change in internal energy of any type of a gas is going to equal the heat in minus the work done by that gas. Okay, now this change in internal energy just means the energy of the individual particles. So we got to change in energy of the particles. Now that might be temperature, it might be any other number of different things, but the total thing that is important here is we're talking about the total change in energy. Q is just like what we've been dealing with for the past few days. Q is the amount of heat. Now normally we're going to assume that the heat is added. That's why it is positive in this situation. And then minus W, this is work done by a gas. Okay, so the total change in energy is going to be increased by heat being added or decreased by work being done by the gas. Right, that work could be done by a gas in terms of like a gas engine where you would explode gasoline in the presence of oxygen to cause the free expansion, which is going to force a piston. All right, so that is how you can get work out of the internal energy. Okay, now this is the generic term, this is a generic sense, but it's a very far-reaching situation. It's important to know what's going on for this part here. Right, now, a couple of things I want to go to quickly here. First thing is some new terminology. Okay, we are going to be talking about a lot of situations where there are going to be, pardon me, changing different variables that are going on here. All right. Now, there are going to be some things that I'm going to need you to know, and to know means literally don't look it up. You should have a solid grasp on this. All right, if we talk about anything that is ISO anything, that means that that individual variable is going to remain constant. All right, now, the four that are going to be important to know here. Isothermal. Now, this one should be pretty simple to work out. Same thermal, same temperature. So that means that this process, if we're talking about an isothermal process is going to happen at a constant temperature. All right, it is not going to be changing at all. All right, so isothermal means that it is going to be happening at a constant temperature. Isobaric. All right, you're going to have to reach back into the memory banks to go back to chemistry. The tool that would be used to measure pressure would be called a barometer. So isobaric means that the barometric pressure is going to remain the same. So isobaric means it is at a constant pressure. Okay. Now, the next two are actually the same thing, but it's two different ways of saying it. We've got isochoric and isometric. You may also see this as isovolumetric. You will not see this one very often at all. Most of the time, physicists are lazy enough, we're going to short it down to what we can use quicker, which is either going to be isometric or isochoric. In all of these cases, every one of them means the same exact thing, which means we're talking about some process happening at a constant volume. All right. So, we will talk about some other terms that are going to mean different things throughout this, but these are the ones that you definitely need to know. Now, the next thing that we're going to talk about is the situation of what is called a PV diagram. A lot of times what we are going to be working with between this chapter and the next is going to be what's called a PV diagram. A PV diagram, well, it's a diagram or a chart which has pressure going up the vertical axis and volume going across the horizontal. All right. Now, the reason that I jumped straight from work into thermodynamics is that this is actually going to have a solid value or a solid use from one end to the other. Now, when we're talking about pressure, pressure is always measured in units of newtons per meter squared or pascals. Okay, we might be dealing with kilopascals, but for the most part it's going to be in newtons per meter squared. When you're talking about volume, you're going to be using units of meters cubed. So, let's say that I am dealing with an isobaric situation here. In other words, my pressure remains exactly constant. You can tell it's constant because we have a horizontal line here. Right? There is work being done for this volume to expand from one value to the next over this constant pressure problem. So if I were to look at the area underneath here from my initial volume to my final volume, in this situation it's actually pretty simple because, well, we got a nice little square. I don't have to do any type of integration to it. So if we were doing the area of a square, it would be length of side 1 times the length of side 2. So the length of this side is going to be measured in meters cubed. So let's just do a basic unit analysis here. So we're going to be multiplying a volume, because that is going to be this length of the side, by a pressure. Alright, so volumes units are going to be in meters cubed. Pressures units are going to be in newtons per meter squared. Alright, now if I cancel out what I can here, I've got meters squared, so I can take meters squared out of the top and limit that down to meters to the first. So if I multiply volume times pressure, I end up with units of newtons times meters, which, if you remember back far enough, that is 1 joule. Okay, so in essence, when we're dealing with these PV diagrams, which are going to be an integral part of what we're doing over the next few weeks, when you take the pressure times the volume, you're going to get work. So this area enclosed here is your work done by your gas. Okay? Now, if we take the situation, instead of having a nice isobaric situation right here, and instead we draw up a new PV diagram, PV with some type of a curve. This is where the integration stuff's going to come back in. So, we already know that multiplying the pressure by the volume is going to give us our amount of work done. In this case here, the work done equals the integral from your initial volume to your final volume of your pressure by your dV. Okay. Now, we might do a couple of problems with this, but I'm really not too concerned in this set altogether. But if we are looking at a PV diagram, by determining this, you can determine the amount of work done by your gas. Okay? So, one thing that is very important to remember in this, though, is this is a path-dependent situation. Alright, I have a visitor. Give me one moment to get this squared up, and it will be pause and break. Sorry about that. Had Mr. Mahoney walk in on me. I wanted to make sure there wasn't anything I was in trouble for. Alright, now, this fact that it is path dependent, do not worry about it too much at this point. We will talk about that a little bit more at a later date. Okay, I just wanted to throw that out there because that may show up, not on a test or a quiz, but it might show up on a homework problem later. Or if you read through your book, there are a couple of example situations that it talks about involving which one is going to have more work. Even though the endpoints are the same, it is going to determine exactly how much work is done based upon the shape of that graph going between there. Okay, now, the next thing that we are going to talk about here are some special cases of the first law of Thermo. Okay, now a lot of these are going to refer back to the PV diagrams that we were just talking about, but if you want to follow along in your book with what we're doing or what I'm going over, it is page 491 in your text. Okay, now the four special cases are all of this same exact equation. The change in internal energy of a system equals the heat added in minus the work done by that gas. So, the first situation that is of a special interest to us is what's called an adiabatic process. Alright, anytime that you have an adiabatic process, now I'm going to first start by saying it is insanely difficult to get yourself to a perfectly adiabatic process. This is more of an ideal, kind of like along the lines of what we talked about with the black bodies in black body radiation. Right? In an adiabatic process, it happens so fast in a well-insulated environment that no energy is lost as heat to the environment. Okay, this is an idealized situation. Okay, this does not really happen, but we can get it to that simulation. So, the other part of this is if it is not lost, it is also not gained as well. So what that's going to do is something to this equation right here. What we are doing is we are capable of eliminating out this Q, because it is happening so fast that there is no heat transfer. It's not going in, it's not going out, so that means that that Q is going to go to 0. Now, in other words, that means the change in internal energy in an adiabatic process is only going to be due to any work done by that gas. Okay? So literally, the internal energy is only going to change based upon the work done on or the work done by the gas. It will increase. The change in internal energy will increase if work is done on the gas. The change in internal energy will decrease if work is done by the gas. Okay? But nothing too crazy on that one there. All right, now the key thing to remember here, adiabatic is idealized. It is not going to happen like that. We can get close to it, but it is very difficult to get it to happen so quickly that it will indeed not allow any heat in or out. We can have good insulation, but to have perfect insulation is almost impossible. So with that in mind, well, it's very difficult to get. 2 reasons behind it. The speed is infinitely fast. And the insulation is infinitely good. All right, we can come close, but it's very difficult to actually get to an adiabatic process. Okay, so this is special case number 1. Special case number 2. Come on, that's not a 2. 2. All right, special case numero 2. In special case number 2, we've got constant volume processes. All right, in a constant volume process, otherwise known as an isometric or an isochoric process, CESS. I'll show you graphically what's going on here. Pressure, volume. Now, if we're having a constant volume process, that means the value for volume is going to stay exactly constant. So whatever I graph for volume is going to be in a perfectly vertical line here. The pressure will change from some initial pressure to some final pressure, but the volume is going to remain exactly the same at some level V. Now the one thing you should be able to notice from here, we've got no area. You can't integrate under a single point. And also, where do you integrate up to? Because all of it is on the same exact line. So literally, what this means, if you have no area, that means you have no work. So we start with that same exact equation for the first law. The change in internal energy equals the heat gained minus work done. So, in this case, we've got no work. Work goes to 0, so that means in a constant volume process, the change in internal energy is going to be equal to only the amount of heat added in or the amount of heat separated out. So literally, change in internal energy is only going to be due to the heat in or the heat out. Nothing else is going to change it. Okay? Now the third one is what is called a cyclical process. Now in a cyclical process, that means that you have some type of a repeating cycle. So, you're going to go from A to B to C to D. There may be more points, there may be less points. But in general, I like drawing it as a situation like this. Right? Now, what I'm going to do here, I'm going to draw up once again a PV diagram. but I'm going to draw up a cyclical process. Right? I'm doing isobaric and isometric situation here. All right? So, let's say we're going A is here, B is here, C is here, D is here. You go from A to B, from B to C, from C to D, from D back to A. And you're going to repeat that cycle over and over and over and over again. Right, now notice what we have here. There's going to be some area that is surrounded by your cycle. This area is going to be the work. Now, if you were to look at this exact situation, in order to start at a lower volume and go to a higher volume, we're staying at the same volume here, I apologize. You go at the same exact volume, but you go from a low pressure to a high pressure. The only way to do that is to add heat. When you go from a low volume to a high volume at a constant pressure, that means you have to add heat. When you go from a high pressure to a low pressure at a constant volume, you lose heat. From a high volume to a low volume at a constant pressure, you lose heat. Now, in the case of a cyclical process, we've got a different situation that's going on here. All right. Now, what ends up happening here is the change in internal energy is going to be zero. Literally, what's going to happen is the heat that you put in gets literally turned into work. So work is either being done on the gas or work is being done by the gas at all times. Right? So the amount of work that is getting done is equal to the heat. Now, we will talk about several of these cyclical processes in the near future. But just know that the work is going to be equal to the amount of heat that you get in there. Okay? Now, the fourth situation, right, is what's called a free expansion. Now, the one thing I want you to know right off the top here is, once again, we're talking about an idealized state. To be totally free is almost impossible. To be totally free means that there is absolutely no impedance. All right? We cannot get this. If you were to take a air tank, a compressed air tank, and fire a .22 round at it, you would get a very quick expansion of that gas, but it would not be free. All right? If you were to take a carbon dioxide tank or a can of Axe body spray and hit it with an axe, you would get a very fast expression of the gas, but it would not truly be free. Okay? Now, in the case of a free expansion, what this means is the internal energy of the entire system is going to equal zero. In other words, the heat is all going to be dissipated in the fact that it is expanding. There's going to be no work because there's nothing to press against. Literally, it throws everything to zero. But the way that we write it out in most cases is this guy right here. The change in internal energy is going to equal zero. All right? Now, What I would recommend for you guys is to look at pages 491 to 493. Make sure that you have a solid understanding of what's going on there. Right. Now, the remainder of the chapter I've already done in the previous lecture on the video. There will be one more assignment, but I want to make sure that you guys are good on concept first. So, come back with any questions that you have. Please email me. I've sent test emails to every one of your accounts to make sure that you guys are good to go for this. So please, email if you have any problems, any questions, any situations that you're confused about. And remember, you should be having problems. This is a college sophomore course. So if you have any issues, let me know. Once I am sure that you guys are solid on the concept, we will go on to the math portion. So let me know if you have any problems. Best of luck, and talk to you soon.